Okay, hi everybody. So in this video, now that we've discussed all of the equivalent statements in the inverse function theorem, let's see why that theorem might be useful. So let's consider the following example. Here I've got a 3 by 3 matrix A whose first row is 2, 3, 4, the second row is 2, 3, 4, and the third row is 2, 3, 4. And oftentimes a very fundamental question in linear algebra is, does matrix A have an inverse? Maybe we don't even care what the actual matrix for the inverse is, but in order to use some results or some theorems, we would want to check first of all to see if A does have an inverse. So here we've got this 3 by 3 matrix, and we'd like to state whether or not this has an inverse matrix. So there are lots of different ways that you might be thinking about this. So one way that we could say this is, we showed before that if A has an inverse, then we know that the columns of A would have to be linearly independent, and vice versa. If A does not have an inverse, then the columns of A are not linearly independent. And so this notion of whether or not A has an inverse, we can boil this down to looking at the column vectors of A and whether or not they form a linearly independent set. So here, the column vectors are all scalar multiples of each other. And so, for example, we can see that A3 can be written as a linear combination of the first two column vectors. In fact, I don't need A2 at all. Just multiplying A1 by 2 gives us A3. So the column vectors of A are not linearly independent, and that would be enough, therefore, to say that A does not have an inverse. We could pick another statement such as, okay, if we can show that A is not row equivalent to I3, then that would be enough to also show that A does not have an inverse. And if we perform two row replacement operations on matrix A, namely replace row 2 with row 2 minus row 1, we would get zeros. Doing the same replacement on row 3 would give us zeros. So we can see that matrix A is row equivalent to a matrix that has two rows of zeros. So therefore, it's not going to be row equivalent to the identity matrix. And if A is not row equivalent to the identity matrix, then we know that A is not invertible since those two statements are equivalent. We can choose any other sort of statements from that long list in order to show that A does or does not have an inverse. So we could similarly look at the columns of A, which are just scalar multiples of each other, and we do not span all of R3. A does not span all of R3. In fact, the only vectors we can get in the span of this matrix would be that have B1, B2, and B3 all equal to each other. So because the column vectors of A don't span all of R3, that would also be enough to show us that A does not have an inverse. We could also take a look at the transpose of A and see that that does not have an inverse, and therefore A would not have an inverse. And there are tons of ways of doing this. So depending on the circumstances, you might be able to identify one of those key statements from that list to easily show that that one statement is true or false, and then you instantly get a whole slew of other statements that you know have to similarly either be true or be false. So this is a nice recap of a number of the notions that we've been discussing so far this semester, dealing with inverse matrices, linear independence, span, solution sets to equations, and so on.